Smooth like butter, AP Calculus students. It is homework for 3.4.3. We are doing today problems 174 all the way through problems 181. We are not going to do 175 or 176 part B. So, with that in mind, let's just go for it. 3.174 asks us to sketch a graph of this function. F of x is x times x minus 1. And use that graph to sketch a graph of the slope function. Honestly, this is probably a best job for calculator cam to do for us. Let's go ahead and clear this out. I wonder if I can make this any brighter, I suppose. Maybe turning the light on? No, that doesn't really help too much. Let's just go for it. So we need this to be x times x minus 1. I suppose we could expand that if we wanted to and graph that, but so the base graph is going to be that little parabola right there. So we'll make a sketch of that graph. I'm going to do that over here on my underneath calculator cam on my paper. You'll see it in just a moment here. I'm just going to sketch that. Looks like it's got zeros at 0 and 1 and has a pretty easy to predict parabola shape. Actually, we probably knew that from the, the more I think about this, we didn't need to graph it at all. I could have told you from the actual function that it has a 0 at, well, let me try drawing that again. It's going to have a 0 crossing at 0, and then again at 1, and then away it goes, up like that. Now, as far as the derivative graph goes, the slope is going to be negative, and it's going to stay negative up until the point when it hits 0 at, looks like 0.5, right there in between 0 and 1. Then it's going to go positive again. So I believe it's going to be 0 at 0.5. It's going to be negative before that and positive after. And we kind of have an idea going on that the derivative of a quadratic graph will be a straight line. And so that's what I think the slope graph looks like. There we go. We're not doing 175. 176a, we're going to evaluate the following limits. And it does give us a hint to review problem 392 first. But we're just going to go for it. Let's see. I don't have much room to work with here, but maybe I can work off to the side here. Yeah, that's what I'm going to do. I am going to take this top expression and expand it out, which I think is the thing you should be able to do. So x plus h to the 5th power. Oh, oof. You know what, actually? Pass. I had not looked at that until this point. 392. Let's see. Well, let's take a look at what 392 says. I'm actually kind of curious. My instinct, by the way, is just to note that this is just the graph. That would just be, this is just, I just want to point this out. This is just the derivative, f prime of x, when the original function is equal to x to the 5th power. That's kind of what I'm leaning towards on this problem. But let's take a look at what 392 says. I think that's probably what we were supposed to get out of that problem. Let's go back in time, way back in time, all the way to 392. Here I am doing my little cat paw thing. 392, 392, 392, 392. All the way back in 392, we had been asked to, While using the definition of derivative, Lulu used the following limit. For what function was she determining the derivative, and how can you tell? Okay, so way back in this problem, what we were supposed to notice is that she was just doing 6 times x squared minus 5 times x plus 3, which you also see right there. So the takeaway on this problem was that f of x is equal to 6x squared minus 5x plus 3. Of course, once you know that, the derivative is incredibly easy to find because you can just use the power rule. F prime of x is 12x minus 5. So what we're going to have to do, go ahead and fast forward this video because I have to go all the way back to that problem we're just working on. Because as much fun as expanding out x minus h to the 5th freaking power is, I think it would be much, much more fun for us to just write that, just identify that we're talking about x squared or something like that, x to the 5th power, and do it that way. Let's go ahead and find this problem. I feel like I'm almost there. Almost there. Here I am. Okay. There's a version of this where that went a lot faster, but here's how we're going to do this. All we need to do is realize that the original function here is x to the 5th power. And the derivative of that is just going to be f prime of x equals 5x to the 4th. Now, it is true that if you were to go and do this by expanding out x plus h to the 5th power, everything would cancel out except for 5x to the fourth. You can try that on your own if you don't believe me. I didn't assign question B, but I can tell you right now that it's actually going to be pretty easy to do because this is just f of x equals 2 times the square root of x. That's all the original function was. So f prime of x would be 2, I got to think about this one for a minute, over 2 roots of x. In other words, just 1 over the square root of x. That would be the answer. Okay, we had done 3-177 as a different video, which I'm going to upload separately, so I'm going to skip that problem for now. Let's talk about 3-178. Let's talk about end behavior of these functions. We're probably allowed to use a graphing calculator for these, but, well, as far as I know here, this first one for f of x, I noticed that there's a 2x squared on top. Let's get you going here. And a regular old x on bottom. So this is going to be a slant asymptote because the degree on top is different than the degree on bottom. So as far as finding the end behavior function, we're going to actually have to do the division then. So let's do that. If we do the division of 2x squared minus 3x plus 1 over x plus 2, we can go ahead and put a, let's see, got to have a 2x on top here. And that gives us 2x squared plus 4x. Then we subtract that. These cancel out. Negative 3 minus 4 gives us negative 7x plus 1. We'll go ahead and do a minus 7 right there. And that's going to be negative 7x minus 14. And we subtract and get, it's going to be positive 13. But it doesn't matter what it is because that's the function. There is going to be a remainder of 13 over on here, but we don't really care about that. 2x minus 7 is going to be the line. Now, if you want to, a good exercise would be to graph this original ratio right there, and then also graph 2x minus 7, and I think you'll see it happen. Maybe it might be worth doing that right now in the calculator. You can skip ahead in this video if you're watching it later on after the fact. So the original function is fraction 2x squared minus 3x plus 1, and on the bottom is x plus 2. And we said that 2x minus 7 was the end behavior function. What's cool is if we graph this, what we should see is some sort of a, there she goes. Actually, it might not show up on this window the more I think about it. There we go. There's your original function. We're not going to see the bottom half of it, I think. But then 2x minus 7 is going to come through here and do the end behavior function. So you don't see it nicely on this graph so much, but that's what's going on there. There's going to be a slant asymptote there. Let's look at B for a minute here. Really, we're thinking about what's going to happen as x approaches infinity. The problem here, this one really won't have an end behavior function. And I'll tell you why. Let's think about what's going to happen as x approaches infinity on this graph, because we're thinking about end behavior anyway. So what's going to happen is that 1 over x will basically become 0. 1 divided by large numbers just gets closer and closer to being 0. The problem here is the sine of x. Sine of x doesn't really have an end behavior function because all sine does is fluctuate constantly between negative 1 and 1. That's all it ever does. As x approaches infinity, sine just keeps doing that same thing. So this one doesn't have any. There is no end behavior function on this one. All you would ever see is a sine value being added more and more, being added 0 too as you get closer. So it'll just be a sine wave. I suppose if you wanted to get an answer here, maybe y equals sine of x might be a good end behavior function because it's just going to be the 0 there, but that would be it. Now this one, this is interesting. If we start plugging in values of infinity, let's think about h of infinity here in this problem. You get sine of infinity over infinity. Now what you got to remember is that this number is only ever going to be 1 or negative 1 or something in between constantly over time. However, infinity on the bottom of this function is going to mean that this whole fraction is just going to divide out to be basically 0. And so the end behavior is y equals 0 right there. There's going to be a horizontal line that graph approaches over time. This graph is going to look kind of like a springboard. It's going to look like this. It's going to approach a y equals 0 as you go further and further towards infinity like that. Okay, next page. Here we got in 179, we are just solving for x in some functions. This is just kind of practice for solving equations because that's a thing we still have to be able to do. Now, A is incredibly easy. It's basically a middle school or Algebra 1 problem. All we got to do here is rearrange some things. We would have y minus 8 equals negative 10x. And x would then equal y minus 8 divided by negative 10. And I think that's all I would want to do in that problem. B can get a little tricky, though. So let's look about B for a minute. We got y is equal to x plus 4 squared. And our objective here is to get the x to be by itself. What you might want to do is try expanding out that x. It would be x squared plus 8x plus 16 equals y. Now, in order to get x by itself, that's going to be pretty difficult to do the more I think about it. Now, a really common trick we can do in these cases is to get all the x's by themselves. Y minus 16 would be equal to x squared plus 8x. And then we could factor an x out on the left side, x times x plus 8. I'm not sure if that actually gets us any closer to an answer here. Let me think about this for a minute. I should have... x squared plus 8x. You know, actually, the more I think about it, let's go back in time a little bit. I think we could be able to solve this by using a different method. Let's try doing the square root on both sides. Yeah, that would do it. You'd have the square root of y equals x plus 4. And then you could just solve the problem by subtracting 4. X would equal the square root of y minus 4. The thing you got to remember here, though, is there should be a plus and minus in front of this. I'm going to circle this answer, but that'll come back in question E down below. Question C. We have y equals x to the third plus 2. This one will be done pretty much the same way as the previous problem. What we're going to do is subtract the 2 from both sides. Y minus 2 equals x to the third. And we can find x by taking the cube root of y minus 2. No real problems there. And then we got D, which gives us y equals 3 sine of x. In order to solve for x, we're first going to have to divide that 3 over. That'll give us y over 3 equals the sine of x. And then the way we cancel out a sine is we do an inverse sine. So the sine inverse of y over 3 will equal regular old x, and I think that's all that's going to happen there. There we go. Okay, we got our selection of problems there. Assuming no domains are restricted, which of the functions above has an inverse that is also a function? I can tell you right now the answer to that question is going to be A. This is no problems at all. A is a regular old linear function, so A works. However, B will not because of the plus and minus that's going to pop in there. If you think about this, the original function B is a regular old quadratic equation, but when you take the inverse and solve for x like that, what you're doing is flipping that on its side, and that's going to cause a no function situation happen. So B is out. C is okay because that's a cubic function, and cubic functions do have inverses. That would be C also. But D is also out. Sine inverse has this problem where it's not really a function because any input, there's actually several different outputs you can get for that one. We don't want D either. It's just going to be A and C. Those are the only ones that are functions. Question 180. Let f of x equal x to the third minus 3x squared minus 24x plus k, where k is a constant. And the question is, on what intervals is f increasing? So what we're going to do here is we're going to take the derivative. If we think about this question differently, what we're looking for is when f prime of x is greater than 0. That would be the same question, just symbolically instead of using English words. That's exactly what we're going to do. We're going to take the derivative and find out when it's positive. So let's go for it. F prime of x, in this case, would be, if I think about this, this would be 3x squared minus 6x minus 24. That's it. So if we take the derivative, that's what we go. Remember, we're looking for when this derivative is greater than 0. I think a good place to start is to set it equal to 0. because what we'll then do is we'll actually solve this equation by factoring, and then we'll be able to actually find the spots where it is 0, and then we can test to see where it's positive and negative. This is just a quadratic equation, and it's got a positive a value, so we know that it's at least a parabola that's shaped like this. So if the x-axis is going to come through like this, we kind of know that there are going to be 2 places where it will be positive, but that's just kind of a conceptual thing. The first thing I would do in this problem is divide everything by 3. Just kind of factor that 3 out. We would get 0 equals x squared minus 2x minus 8. And that's a thing we can easily factor. Let's see. Things that multiply to 8 and then add to negative 2. How about minus 4 and plus 2? That would work. So we kind of know that our zeros are at 4 and negative 2. So maybe over here in my drawing, maybe this is negative 2 right there. And that is 4. And that would mean maybe the x-axis or y-axis is like that. It wouldn't matter there really much. Now, based on my understanding of parabolas, I kind of already know this is the way it's going to look. But let's just try a little bit of a sine chart to help us out with. We know negative 2 is here. We know 4 is here. What you do here is you test a number, like 0, for example. And you say, okay, if I were to plug 0 into the f prime, would I get a positive or negative number? And you would get negative 8, which is negative. If you were to plug in, like, say, negative 3 for a tester, you'd get positive 9 plus, it would be a positive number. And then it'd be positive over here, too. So as far as intervals on which our original function, this is all f prime, our original function is increasing whenever the derivative is positive. So negative infinity to negative 2 and 4 to infinity. So the correct answer here is going to be that range. It would be the interval from negative infinity to negative 2 union together with 4 to infinity. That's the domain on which the original function is increasing. Let's go ahead and move that over here. That's the answer. And 3.181, we got one of these volume questions. Calculate the volume of a solid created when the semicircular flag at right is rotated about its pole, and describe the rotated solid. So what we're going to do here is we're actually going to take 2 larger volumes and we're going to subtract them. And I think that's the best way to do a problem like this. So we will start our adventure here. Let me move that up just a tiny bit. We're going to start our adventure by realizing that when we rotate this around, we're going to have kind of an outer sphere. But there's going to be kind of a hole missing from it. There's going to be a cylinder in the middle that'll be kind of removed from this shape, because that cylinder will come from the fact that those are all kind of the same height. So basically, if I think about this on a larger scale, the volume is going to equal the volume of the sphere minus the volume of the cylinder inside. Maybe I'll use orange for that to help you kind of visualize what's going on there. So there's like a sphere with a cylinder missing in the middle. The volume of the sphere, I'm going to have to Google it myself. I hope I'm not wrong, but I'm pretty sure it's 4/3 pi r cubed. Hang on just a moment. Let me just do a quick Google search here. Volume of a sphere. 4/3 pi r cubed. I was pretty sure I was right about that one. Now the radius of that sphere is, that's going to be another question we got to answer. What is the radius of this sphere? Yikes. Well, it would be the distance from this center point out here, which, and I know that chunk there is 4, and I know the height is 6. So that the radius there, that's all I'm looking for. That would be 4 squared plus 6 squared equals r squared. Got to use a little Pythagorean theorem to get there. That's going to be 16 plus 36 equals r squared. Let's see, 16 plus 36 is going to give me 16 plus 36, I said. 52, which is not a perfect square number. That's okay. R is the square root of 52. It's going to get cubed in my equation in a minute here anyway, so that's going to be the square root of 52 cubed. As far as our cylinder goes, that's going to be pretty easy to do. That's just pi r squared h, which in this case the radius is going to be the 6 right there, and the height would be the 8. So it'd be pi times 6 squared times 8, like that. All we got to do now is kind of just shake out what this would be. Technically, this answer is done if you're talking about the AP Calculus test, but 4 pi over 3. I don't know what the cube root of 52 cubed is. or square root of 52 cubed. It's going to be 52 roots of 52, whatever that is. Let me just check this really quick. Square root of 52 to the third power. Anything cool? No, nothing nice there. You know, I guess, you could use the decimal version of this. I do know, wow, man, I don't know a better way to write that. Should we just use the decimal version? No, we should never use the decimal version. I do know that the square root of 52 to the third power is equal to 52 times the square root of 52, because that's kind of like two of them together make up 52, and there's one more on there. Over here, this is actually pretty easy. 6 squared is going to be a number times 8. It's going to be 288 pi. I'm just hoping that I can do something there. Oh, it looks like calculator cam's a little blurry. Let me bring her up to the front. Autofocus, please. Get it. Perfect. Now, I'm guessing that 4/3 times 52 is something. Oh, it's not. Okay, cool. Nice. It's that number over 3. Oh, cool. I was pretty sure that 52 divided by 3 was something even, but it's not. So you know what? I'm just going to leave it in its most base form. I'm going to have 4/3 pi times the square root. I'm just going to say, you know what I'm going to do? I'm going to write 52 to the 3/2 power, because that's exactly what's happening here. Minus 288 pi. That's as simple as I want to get with it. You could keep crunching out decimals if you want to, but honestly, the most important part about this problem is the sphere minus cylinder idea. That's what you want to know. Okay, that takes us to the end of this assignment. Hey, I know it got a little spacious in there, so thanks for joining with me. Remember, you are amazing. Thanks for making it here. I'll see you in the next video.